Hello, class. Welcome back for another day of lesson 9.2. We're going to spend our third day and hang in there. I know this stuff can be a little tedious and it's new and challenging, but you're doing a great job so far. We're getting close. I've got two new graphs, new shapes to share with you today, and then we will have seen the full array of possibilities. So just stick with it. If you're having trouble, please don't hesitate to reach out. Let me know how I can help. So we're only going to do two examples. That doesn't mean this will be a short lesson necessarily, because there's a lot to talk about with each example. But we're going to do two main examples, and then if you have your graphing calculator, I'm going to prompt you a few times to try some things on your graph to just kind of make some predictions and see how the graph changes when we change certain numbers. So I think that would be a really good exercise if you're able to do that with me. And so the first one is r equals 2 cosine 2 theta. And I am going to ask again that when you do your homework for this lesson that you please check for symmetry first. I think that again, these graphs are so new that we're still doing a lot of exploring. We're trying to figure out what things look like. And if we know if there's any symmetry involved, then that's going to help us come up with points much more efficiently. So as part of your homework, that's something that I'd like you to do, and I guess I'll call that a requirement. So we know how to do these first two. There's actually a third type of symmetry I'm going to talk about here in just a minute. But let's go ahead and start with the two that we're familiar with. So first, to check over the polar axis or the x-axis, we replace theta with negative theta. So we can do that pretty quickly. So I'm going to say 2 cosine 2 times negative theta. And since cosine is even, that means cosine of negative 2 theta and cosine of 2 theta are the same. So this one ends up being back to the original, 2 cosine 2 theta. And since it can go back to the original, that means it will be symmetric over the polar axis. For the line theta equals pi over 2, we replace theta with pi minus theta. So we'll say r equals 2 cosine 2. We actually might want to do brackets here. And then parentheses, instead of theta, we'll do pi minus theta. And I think I would recommend going ahead and distributing the 2. And when I say the 2, I'm talking about the 2 on the inside here, not the one on the further outside. So then we have cosine of the difference of two angles. And so if we go back to this list of identities that we studied in chapter 7, one of these four should be able to help us out. So since it's the cosine of a difference, it looks like we're going to use this first one here. And so we'll do cosine of the first angle, cosine of the second, plus sine of the first, sine of the second. All right, so that looks a little something like this. And then cosine of 2 pi is 1. So that leaves me with r equals 2 times cosine 2 theta. And then since sine of 2 pi is 0, this term just goes away. And so we're just left with cosine 2 theta. And that is what our original was. And so that means this one will also be symmetric over the line theta equals pi over 2 or the y-axis. Now this is the first one that's been symmetric over both. If you think back to the last assignment, I don't think we had any that were symmetric over both. And so if you were caught into thinking that, oh, if it's symmetric over the first one, that means I don't have to check the second one because it won't be both. Well, sometimes it can be both. And so it's really good to just get in the habit of checking both. I know it does take some time, but I think the payoff is good. It makes the graph a little more clear for us. And then I'm going to add one more. There's a way to check symmetry over the pole. The pole is like being symmetric over the origin. You might remember doing that with rectangular coordinates. Um, and so I didn't have you check this on the last one because none of the ones we did last time were symmetric over the pole, and I felt like I'd already given you enough work to do. But some of them today might be, and so this one's actually really easy to check. You just replace r with negative r. So if I do that, you'll see pretty quickly that this does not change back to the original. You end up just moving the negative over to the other side, and that is clearly different than what we started with. So this one is not symmetric over the origin. We will see one later on that is. We'll talk about how to deal with that. All right, so now we're ready to make it some output values and graph. And actually, I think I'm going to go ahead and skip ahead to the graph, and I'm going to go ahead and put my polar axis like we like to do first. And so that goes towards the right along the x-axis. And then I like to do this. You certainly don't have to, but I like to maybe just remind myself that it is symmetric in two places. So I'm going to put, I'll use a different color here, but I'm going to put dotted lines along the polar axis and the line theta equals pi over 2 just to remind me about the symmetry that we're going to be able to take advantage of in our graph. Okay, so now we're ready to make some values put into our table. And so I think like before, I would recommend that you pick nice and easy numbers. Friendly quadrantal angles like 0, of course, is always a good choice. So 2 times 0 is 0. Cosine of 0 is 1. 1 times 2 is 2. So we could start with 0, 2 on our graph. That'd go right here. Now again, we want to take advantage of symmetry anytime we can. So that means if 0, 2 is a coordinate, shouldn't also pi 2 be a coordinate? And if you want to put that in your table, I would just put them next to each other and group them together. If you don't even want to add it to your table, that's probably okay. You can just use symmetry to justify that value. So then I might move along to say like pi over 2 would be a great choice. And so 2 times pi over 2 is pi. Cosine of pi is 0. 0 times 2 is 0. So that doesn't really help us on our graph. It just means, maybe it does a little bit. It means we have a point right there at our pole. Symmetry doesn't help us get another point in this case. So then maybe the next thing I might move along, even though pi over 4 isn't traditionally a quadrantal angle, if I multiply it by 2, it becomes a really friendly angle. Pi over 4 times 2 is pi over 2. And I know the cosine of pi over 2 is 0, so this gives me a 0 here as well. And I say as well, but I'm realizing just now that I made a mistake, so I'm going to fix that real quick. Back to pi over 2. I don't think I doubled the 2 here, so let's try that again. So if I double pi over 2, that gives me pi. Cosine of pi is -1, and -1 times 2 is -2. And so if we take a look at that on our graph, I'm going to go back and erase this one. And if I have pi over 2, -2, so pi over 2 normally tells us to go forward, but we're going to go back 2 places. So how about right here? And then again, if we know that we have symmetry over the polar axis here, that means there should also be a point here. And I'm thinking that's probably, if I did 3 pi over 2, I would have gotten -2, so I would have gone backwards. So I'm kind of thinking the point over here, 3 pi over 2, gives the same value as pi over 2. Okay, so that takes us back to our pi over 4, which I do believe is 0 this time. That one is correct. So that gives me a point here after all. So then we kind of look in our picture trying to figure out what's going on. Like you could almost make the case that we've got a circle here, but I think before we do that, we probably ought to see what's going on maybe at pi over 6 or pi over 12 or one of those places. And so I'm kind of thinking that pi over 6 might be a really good choice for us. And the reason I like pi over 6 is because, again, I'm not actually finding the cosine of pi over 6. I'm doubling that. So I'm finding the cosine of pi over 3. And that's a really friendly number in 1/2. And so I'll have a half times 2. So I'm going to get it looks like a 2 here. No, take that back. Half times 2 is 1. There we go. And so now I'm going to plot that value. Pi over 6 is 1. So that's going to put me here. Now I can use symmetry to help me out. Kind of thinking if I flip over this line, that's going to be negative pi over 6. Will also be 1. Also, if I flip over this line, the vertical line here, at 5 pi over 6, that one's also going to be 1. And then at 7 pi over 6, that one's also going to be 1. So I'm starting to get a little bit better idea of what's going on here. I think I'm going to try maybe one more point. And remember, the good news is 1 point can often lead to 4 points. So I think the payoff for that might be worth it here. So I'm going to try pi over 3. And normally the cosine of pi over 3 is a half, but remember we're doubling it first. So now we want the cosine of 2 pi over 3. And that'll be negative a half times 2. So I think that's going to be negative 1. And so if we go back to our graph here, 2 pi over 3, if I'm going negative 1, I'm going backwards. So I'm actually going along towards 5 pi over 3. But since I have symmetry, that means I should have a point that goes towards 4 pi over 3 here. And then pi over 3 here. And then also at 2 pi over 3 here. Okay, so now you might be wondering if if I've never graphed this before, how do I know where to start? Well, you always start with like 0. Okay, pretend like you're starting with an angle of 0 and you're sweeping around towards, let's say, like 2 pi, 1 revolution. Well, if I start at 0, I would start right here. And so then the next place I would go would be to pi over 12, and then pi over 6, and then pi over 4. So the best way to connect the dots is to follow that pattern. And so it's going to maybe look something kind of like this. All right. And so we have a shape that we refer to as a rose. And we would call this a rose with 4 petals. And yeah, that's kind of cool. It's kind of neat and certainly different. I think this is our first rose we've encountered in math class. And so what I'd like to do now is try to figure out, well, what's the pattern that we should be looking for a rose? And like, what are these numbers up here doing? Like, are those 2's important? Are those 2's needed to be a rose? What if those numbers change? Is it still a rose? Is it a different looking kind of rose? And so if you have your graphing calculator, I would encourage you to get that out now. And I'm going to prompt you to try a few things on your graph. And so I would encourage you to maybe try all 3 of these in succession. So go ahead and try to graph the one that we just did by hand and see if you get a matching answer. And then after you have that, you might consider doing it on the same graph, or you can either clear your graph and just do the next one, or you can do like R1, R2, R3 and graph them all on top of each other and see what that looks like. But if I were you, maybe just pause the video for a second, and maybe you could try this on your calculator and see if you make any observations. Okay, so assuming you've had a chance to do that, let's see if your graphs look similar to mine. So here are the graphs that hopefully you came up with. It looks something like this. You'll notice for all of these, they still look like roses. They still have 4 petals. So it looks like what's happening is we're just changing this outside coefficient. And it looks like that coefficient is the length of the petal. And that length also makes the petals themselves a little bit bigger, like in area. And so if we go back to that first one, you'll notice we went out 2 units from the pole. And then when this was 3, it went out 3 units. And when it was a 4, it went out 4 units. And so what it appears is happening is that that coefficient out front is changing the length of the petal. So what I'd like to do now, and I guess, sorry, that's what I'm trying to show here on this slide, is so if we have an equation of this form, r equals some number times cosine 2 theta, that should be a rose with 4 petals, and that front number will be the length, that front coefficient will be the length of the petal. So now what I'd like to do is change the cosine to sine and see what happens. So we're not going to have time to do one by hand like this, but we have our graphing calculator, so let's do a little bit of exploring. So maybe graph the exact same graphs and change cosine to sine. And here, again, I would encourage you maybe just to pause the video and try this on your own and see what happens. And assuming you've done that, let's take a look and see if you have the same thing that I have. So it looks similar in many regards. It still looks like a rose with 4 petals. It looks like that outside number still affects the length of those petals. But you'll notice like the orientation's a little bit different. So if I kind of go back and forth here, if we look at the cosine ones, you'll see that they're symmetric over the polar axis and the line theta equals pi over 2. And you'll notice like the graph kind of goes above and below what we would call like the x-axis or the y-axis, or to the left and the right side of the x and y-axis. Whereas when it's sine, it's just kind of like all those have been rotated 45 degrees, so that now all those petals are in between the x and y axes. And so that's kind of really all that sine is doing. It's just turning, it's rotating. If you think about, like if we put like a sine graph and a cosine graph together, do you know how it's like the same graph? The only difference is one is shifted over 90 degrees. And so I think that's kind of what's happening here as well. It's the same graph, but only shifted 45 degrees. And you might say, well, wait a minute, shouldn't it be 90 degrees? That's how sine and cosine work. But notice right now, as it stands, is we have a 2 on the inside. So that's acting as kind of like a compression. And so what used to be 90 degrees is now half of that. That's 45 degrees. And so it's just like everything that the cosine graph was just moved 45 degrees. And that is the petal with a sine in the equation. So the next thing I'd like to do is let's, in case I'm kind of wondering, you might be curious, like what happens if I change the inside number. So we know that changing the outside number for both, whether it's cosine or sine, changes the length of the petal. But what happens if I change the inside number? So we have been using 2, but what if I use a 3 or a 4 or a 5 or a 6? And so again, I would encourage you to pause the video and with your graphing calculator, change all these to be 3, 4, 5, or 6 and see what happens. One thing I should warn you of, maybe I should have done this in case you already paused the video and found out on your own, but there is a setting in your window that you might want to change to give you better results. if you tried graphing some of these and you got a picture that looks more like a fan and less like a rose, if you go to your window setting and go to theta step, and I think yesterday I might have, or the last lesson I had suggested you trying pi over 12, and I think that worked okay for the last lesson, but we want to shrink that value. Probably if you did something like pi over 24, that would be fine, but I think I'd rather just exaggerate it to make it, make sure that our graphs look really nice, is change it to something like maybe pi over 48. And what theta step is it's telling your calculator what kind of step should I take before I graph the next point. So what your calculator kind of does is it graphs point to point, and that step tells you like how many angles should the calculator travel before it places the next point. And so sometimes if that step is too big, then when it connects the dots, it ends up looking more triangular or box shaped, or more like a polygon like this. But if you shrink that step, then it makes it look more curved and smooth like it's supposed to. And so if you want to try that, adjust that setting, I think you'll get much better results. And you should end up with graphs that look a little something like this. So again, more like petals and less like fan paddles or something like a ceiling fan. So anyways, it looks like what we're noticing here is that inside number affects how many petals we have. Now, you do want to be careful though. There's kind of a difference to whether the number's even or odd. If the number on the inside is odd, you'll notice that that number corresponds with how many petals. So like a 3 is going to have 3 petals, a 5 will have 5 petals. We could guess that a 7 would have 7 petals, and so on. But you'll notice if that inside number is even, it actually doubles the number of petals. So a 4 doesn't mean 4 petals. A 4 means 8 petals. And a 6 doesn't make 6 petals. A 6 makes 12 petals. And so I'm trying to summarize that here on this chart here. So again, a rose can be formed with either a cosine or a sine. The A in either case is the length of the petal. The N tells you how many petals there are. If N is even, you double that number and that tells you how many petals there are. And if N is odd, then you will have that number for the amount of petals.